Well, in the midst of this abstractness, we're going to write a coordinate proof. And so we have an object here. It's on the coordinate plane. I see here at the origin, we've got point A at 0, 0. If you notice here on point B, it is 0 plus x is the x coordinate. Well, that makes sense. B is the y coordinate. If I go down here to point D and look at D, that's A units down the x-axis. So its coordinate is A, comma, 0, which means that C up here, I guess maybe I could be marking on this if I wanted to. C right here then is, if you think about it, is A plus x, comma, B. And then we have a point X, which is A plus x over 2 and B over 2. We're given that information. So let's see. What are we asked to do? Write a coordinate proof that triangle ABX, this little triangle here on the left, is congruent to CDX, which is this triangle right here. Are you ready? Well, let's do it. All right, so we're given that we got two triangles. And we got, of course, all this other thing with these coordinates. So triangle ABX and CDX, this is what we're given. We're asked to prove that those two triangles are, in fact, congruent. So let's get about it. Okay, so the midpoint of AC, using the midpoint formula. So let's see, the midpoint formula is x1 plus x2 over 2. Well, let's say x1, we got 0. x2 plus a plus x. So we see that right here over 2. And then y1, y2, well, y1 here on AC, which is what we're talking about, is 0. And the y coordinate is B, also over 2. And if we simplify that, we've got A plus x over 2, B over 2. And then when we look at the midpoint of BD, well, x1 is 0 plus x, let's say. And we're BD, okay, there we go. BD, BD, BD. And A. And our y coordinates then are B and 0. And that simplifies to A plus x over 2, comma B over 2, which is the same as AC, Shazam, and which is the same as we see as the coordinates for x. Isn't this fun? Okay. So since that's true, since B is located at A plus x over 2, comma B over 2, it is the midpoint of AC and BD. Well, Shazam, how about that? We could probably recognize that by looking at it. So, by definition of the segment bisector, AC bisects BD, AC bisects BD, and BD bisects AC. So guess what? If they bisect each other, then BX is congruent to XD. So these two are congruent, right? And AX is congruent to XC. So these two, AX and XC, are congruent. Well, we got two sides that we can identify being congruent to each other. You know, I bet if we could find a measurement for AB and CD, I bet we could prove that those two triangles, ABX and CDX, are congruent by side, side, side. What do you think? So let's go through it. I said we've already determined that this is congruent to this and this is congruent to this. All right, so CD is equal to the square root of A plus X because it got x2 minus x1 squared over y2 minus y1 squared over A here, CD, we're talking about CD, squared plus B right here over, plus 0 squared, and that simplifies to, because I got an A and a negative A, just x squared plus B squared, okay, that's CD. That's equal to x squared plus b squared. What about AB? Well, AB, x2 minus x1 squared. Okay, well, let's say that's x2 and 0. There we go. Excuse me. Yeah, okay. Plus b minus 0. Okay. So that's just going to equal x squared plus b squared. And then our y coordinates, b0 is just, okay, so, well, they're equal to each other, aren't they? CD is x squared plus b squared. AB is x squared plus b squared. So these are congruent. All three, we got all three sides. We got congruency between all three sides. Therefore, CD is congruent to AB by the definition of congruency, and that means that triangle ABX is congruent to triangle CDX by side, side, side. Whew, it's pretty abstract. I think my head hurts.